is Nicolas Regnault. Take it away.
Thank you. So first, let me thank the organizers for putting up this workshop. Unfortunately, it's not a pleasure to be here at home. I would prefer to be somewhere else, but hopefully the situation will change soon. So today I will talk about some recent work we have done on fractional chiral hinge insulators. This work was mostly done by two people, Anna Ackenbroich from Garching, and she did really all the heavy lifting when it comes to the Monte Carlo simulation that you will see today, and also Anna Hudomal from Leeds, and she helped us a lot for the exact dimensionalization part. And also the two older people on the right-hand side, Norbert Schur and Andre Bernabik. And you can find more details about this work in this reference here. So let me give you an overview of what we wanted to achieve in this work. So we know a lot about topological order in 2 dimensions, and we have one concrete experimental example with a fractional quantum Hall effect. Now, if you want to move to a 3-dimensional system, we have several models or several concepts, mostly using simple spin Hamiltonians, which are like the generalization of the toric code. We have all the what goes beyond topological order in 3D, namely with fractons. But what we were interested in is to have a macroscopic electronic models like we have for the fractional quantum Hall effect. And the idea was to use some intermediate step between these two situations, so the fractional quantum Hall and the fractal world, by considering the higher order topological insulators. So here in the middle, you have the experimental measurement of the hinge mode in bismuth. So remember, a higher order topological insulator, the bulk of the system is gapped, the surface are gapped, but the hinges or the edge of the edge modes are gapless. So the simplest model in 3D for higher topological insulators without any interaction, you do have chiral modes at the hinges. So from this perspective, it looks like what we have in fractional quantum Hall effect on quantum Hall effect. So this is a pretty nice starting point to wonder what will happen when we will turn on strong interaction in such a system. And as usual, the simplest way to try to probe this physics is to build a model state for a fractional chiral hinge insulators. So let me explain the model that we have used. And first, the non-interacting model. So the model that we will use was developed by Schindler and collaborators in 2018, and it can be summarized like this. So you have here the time binding model that we use for this chiral hinge insulators. It has 4 atoms per unit cell, and you have several couplings, and it can be seen as the charge pump version of the quadruple model, which is the simplest higher order TI you can build. So let's take a look at the bulk of the system, which is depicted on the left-hand side with this cube, and look at the dispersion relation of this model with the energy as a function of the momentum kz along the vertical direction. And as you can see, the bulk is gapped. Now, let's say I take a situation where you have boundary conditions in every direction. Let's say I take OBC in the x direction. So now I have 2 surfaces here in green, and I can see where they are in the band structure here. So these green points. Now you see the surfaces are still gapped. But now imagine that I have OBC both in the x and the y direction. And then if you look at the energy spectrum, then you have the 2 chiral modes in red and blue that correspond to the 4 chiral hinges that you have going along the z direction. So these hinge modes are like the chiral mode that you have for the integer quantum Hall effect, but the surface are not identical to the integer quantum Hall effect. The system is protected by the C4T symmetry, And the only thing that it guarantees is that the number of hinges, the number of modes per hinge that you have is conserved mod 2. And you can see that by, for example, trying to gap out the system by adding quantum layers on the 4 surfaces. And you will see that you cannot make these modes disappear. You can only change them by 2 units. So that's the non-interacting model that we will use as a starting point. But how do we build an interacting version of it? Well, what we do is we use the same recipe than how we go from a chain insulator to a fractional chain insulator by using a Gutzwiller projection. So imagine here you have a simpler model, which is just a chain insulator like the Haldane model in 2 dimensions. So your system, if I look at the energy as a function of K, has 2 bands, and you have exactly at half filling, so your valence band is fully filled. And now you take 2 copies of this system, one you dub spin up, the other one that you dub spin down, and you imagine that you have a strong on-site repulsion between the up and the down electron. So the FCI, fractional chain insulator phase, will emerge if the interaction is strong compared to the band to the gap of the system and the bandwidth. And you can build a very nice model wave function in the large U limit. So basically, the large taking U to infinity, the subatom to infinity, will forbid to have more than 1 particle per site. And so the only degrees of freedom that you have left is basically to decide, because you're at half filling, so you have exactly 1 electron per site, is if the electron has a spin up or a spin down. And you can actually write down the model state by using the Gutzwiller projector that you apply on the tensor product of the 2 copies of your chain insulator. And that was studied in this paper by Vishwanath and collaborators. You can extract lots of information from this model state. You can probe it by entanglement entropies. You can look at the topological degeneracies, for example, and see that it's exactly the same physics that you have for the Laughlin 1/2 state. Remember that we are dealing here with a spin degree of freedom. So for the fractional Chiral Hinge insulator, we will follow exactly the same recipe. Namely, we take the ground state of the non-interacting Chiral Hinge insulator at half filling. We take 2 copies of it, and that we call a psi up and psi down. And we take the tensor product and we perform the Gutzwiller projection. So overall, we have exactly 1 electron per site, only the spin is the only degrees of freedom. So the charge is completely frozen, only the spin might fluctuate. This is a model wave function that we can actually put on a computer, and we can try to extract some information about it. Namely, we can use Monte Carlo simulation, for example, to compute the secondary entropy, which is usually way easier to compute from Monte Carlo than the fundamental entropy. We can look at the spin fluctuation, and if we are able to generate different states that could correspond to different topological sectors, we can look at overlaps between them. Just briefly, some technical details about how we do the calculation of the secondary entropy. There is this nice trick based on the swap operator where you need 2 copies of your interacting system, and out of it, without entering into the details, you will extract the secondary entropy. The reason I'm showing this slide here is don't get too much hope about the size that we can reach. Remember, we are dealing with a 3D system. And even though the Monte Carlo, in principle, you could imagine that you can simulate a large number of electrons, computing a quantity like the entanglement entropy will still be exponentially complex. And more precisely, it will be exponentially complex with the area of the region, of the entanglement region. And just to give you some scales, this is the number of CPU hours we have used for this whole project. Okay, so now we have our model state. The question is what do we have in it? And the way we can probe it is using as much as we can these entanglement measurements. Remember, there are a few things that we want to characterize. We would like to characterize the hinges of the system. We would like to characterize the surfaces and the 3D bulk. So let's start with the simplest one, which is the hinges. they are 1D system like we have for the edge mode of a Chiral insulator. For that, we can use, because they are critical system, we can use the usual formulation, a result from CFT that tells us, well, if your entanglement region is of size L, a quantity like the entropy or the spin fluctuation will scale like log L. So with this entanglement region. More precisely, we can even have the formula when we have a finite size system and a finite size entanglement region. And if we look at the signal reading entropy, the important thing is the prefactor on this formula is related to the central charge, which is the first characterization, and we expect to be equal to 1 if we have a litigial liquid. And out of the charge fluctuation, or here the spin fluctuation, we'll have the litigial access to the litigial parameter. And if it's different from 1, we do have fractionalization. So just by studying the scaling of these two quantities, we will be able to characterize the 1D system or the hinges. So of course, the hinges, they are not strictly 1D system. They live at the edge of some 3D system. So let's look back at the 2D case, how we can extract information from for the edge mode, knowing that we have a 2D system. So imagine that you take your quantum Hall liquid and you put it on a cylinder, and that you take this red region here as your entanglement region. And let's say you want to see how the entanglement changes when you change the length along the cylinder perimeter. Your entanglement will have two contributions, one coming from the bulk. It's basically the area low that you have here and here. And this critical contribution coming from the red and the blue edge modes. So if I just look at how this entanglement entropy varies as a function of the length NXA, so the length along the perimeter, the cylinder perimeter, then I don't care about the bulk contribution, and will only probe the critical part. So that's what's for the 2D system. And if I can apply exactly the same trick for the 3D, except here, well, I will use this red region here as my entanglement region. And the only thing I will change is the height of this cube in red along the z-axis. The bulk contribution coming from the surface here will not change when I change this length here. Only the critical contribution will change. So let's first look back at the fractional Chiral insulators and what kind of result we get. So here you have the signal reading entropy, and you can fit your numerical results with the formula I've shown you coming from the conformal field theory and extract the central charge. And you get C which is equal to 1 with an approximation around 10%. The spin fluctuation is actually way easier to compute than the entanglement entropy. And you get that the litigial parameter is just given by 1/2. So you do have the fractionation. It's exactly what you expect for the edge mode of the log 1/2 state. Now we can do exactly the same calculation for the fractional Chiral Hinge insulator that I've described. Here I show you for two different system sizes. So in blue, it's a system where you have 2 unit cells in the X and Y direction and 20 unit cells in the Z direction. And for the orange line, you have 3 unit cells in the X direction, 2 in the Y direction, and 20 in the Z direction. And as you can see, if you take the biggest system size we can reach, the central charge that we get is really close to 1. And same thing, the litigial parameter is given by 1/2. So overall, the hinge mode of the states that is built to describe the fractional Chiral Hinge insulators are identical to the edge mode of the log 1/2 state, which is basically the same kind of picture that we had for the non-interacting version. So of course, now the question is, okay, it's fine for the hinges, but what about the surface mode or the bulk? So to probe the either the surface or the bulk, we can rely on the topological entanglement entropy. So remember that for if you take a 2D system, you have for the entanglement entropy, you have the area law that's scaled with the perimeter of the region A, or the entanglement region A. And the first correction is a constant that only depends on the nature of your topological phase. Numerically, there is a very two different schemes, either the Kitaev prescale or the Levin-Wen cut, that allows you to extract this gamma contribution by getting rid of both the area law and any corner contribution with a smart combination of different regions. So you cut your region, your space into 4 regions, and you compute different combination of these regions, and you directly get the expression of the topological term. In 3D, what we will do is to take this cut and extend it completely in one of the directions. So here, for example, on this figure, we have extended the Kitaev prescale cut along the x direction. So first, let's imagine that we have periodic boundary conditions in every direction of the system. If you do the calculation, if you try to extract the gamma, in that case, you get something which is compatible with 0. So that's the value that we have here. It does not depend on the orientation. So here in this figure, the cut is basically translation invariant in the x direction, but you can rotate your cut and have it a translation invariant along the z direction, and you will get the same value for gamma. We check that for 2 different system sizes, the only 2 that we are accessible numerically. The good thing is, if it was a layer construction, just imagine a bunch of Laughlin 1/2 state stacked together, we would expect that this gamma will depend on the numbers of layers, so the size of the system, which is not what we find here. And now imagine that we, in the x direction, this cut terminate on open surfaces. So we take OBC in the x direction. Then what we get is something which is compatible with log of square root of 2. But you have to be careful here, because if you want to compute the contribution for a single surface, then this is the expression that you have here. You have to remove the contribution coming from the bulk, the gamma PBC, and divide by 2 because you have 2 surfaces. So overall, the gamma correction that you have per surface looks more like the half of the log of square root of 2, which is a half of what you expect for Laughlin 1/2 state. And it's a bit puzzling because if you think about, topological order in 2 dimension and abelian ones for this system, you expect either to get gamma equal to 0 or gamma larger than log of square root of 2. And why, of course, we do have still some large error on the extraction of the gamma. Right now, we can safely say that we get neither 0 nor log of square root of 2. So then maybe the naive picture that we get out of this calculation is to say that in the same way, you cannot get strictly Chiral, a one-dimensional Chiral state. You have to see them at the edge of the system. Here, what we did was to take a Laughlin 1/2 state and split it into 2 with a 3D bulk system. So what about it's strange because if there is some topological order, you expect to get some correction coming directly from the bulk. So let me once again repeat the calculation that we have done. Unfortunately, due to the size limitation, there is no way we can extend, we have to extend the cut fully along one direction, because we are dealing sometimes with only 3 or 4 unit cells in the Z direction. Or if you rotate it, it's only 2 or 3 unit cells. So there is no way we can terminate the cut in the bulk. So there's always one direction which is microscopic, so that's scale with the system size. And if you look at this paper, another paper by Vishwanath and collaborators, where they discuss about the typical correction that you expect to the area law for a higher order topological order, the proper way to would have to do to extract the gamma for the bulk would be to have something like a field torus, so a donut inside the 3D bulk that we cut into 3 different regions, A and B and C. Unfortunately, that's not something that we're able to do yet numerically. The next question is about the topological degeneracy. So looking back at the fractional chain insulators and its construction using the Gutzwiller projection, if this is the love-in-1/2 state, you should get, and with PBC, you should get 2 states. So how do you get them? Well, you get them by playing with the boundary conditions of the underlying layers. Namely, you can take your electrons with a spin up and a spin down to have the same type of periodic boundary conditions, namely anti-periodic or anti-periodic. And the resulting system will have the proper periodic boundary conditions. And you can play that in both directions, X and Y. So in principle, you could generate 4 different states, but after Gutzwiller projection, you will see that only 2 are linearly independent. So that's how you recover the 2 love-in-1/2 state on a torus using the Gutzwiller projection. So we can try to play exactly the same game here for this fractional Chiral Hinge insulators. So how many states can we generate at most? Well, we can play with the boundary conditions in every 3 directions. So we use PBC in all directions, which can generate at most 8 states. And let's say if you want to see anything about the surface mode, we can have open boundary condition, let's say in the X direction. And then we generate 4 states. So we can generate these states numerically, compute the overlap by Monte Carlo, and using the overlap matrix, try to see how many linearly independent states we have just by looking at the eigenvalues of the overlap matrix. And that's the result when you take the isotropic limit with full PBC, and this is the same kind of calculation with OBC in one direction. Unfortunately, I would have a hard time to make a strong conclusion about degeneracy here. Yes, we have, in general, 2 large eigenvalues in the reduced density matrix, and much smaller ones, 6 other smaller ones, or 2 other smaller ones if you have OBC in one direction. But clearly, it's not enough to claim that degeneracy is twofold. If you want, if we require to make a proper finite size scaling, which is definitely out of reach numerically now. So this is not the end of the story. There is clearly some limitation with the Monte Carlo technique, but there's still some very interesting signature that there is some physics beyond what you know from the let's say from the fractional automole effect in this Chiral Hinge insulator system. And that's basically the conclusion of my talk. And here you have the point I've already mentioned. But I would like maybe to emphasize the what we can try to think about the future direction for such a work. Once again, 3-dimensional numerical calculations are difficult, and clearly with Monte Carlo we are almost running out of steam. So there is a need to find for other techniques if we want to probe that kind of physics. We still don't know what is the nature of what we have, the state that we have built. Sure, I'll give you some signature, but it's very hard to make any clear-cut conclusion. And one thing I didn't talk at all is about the top and bottom surfaces. because I always took paradigm boundary condition in the Z direction. If you know a little bit about the Chiral Hinge insulators, you know that the top and bottom surfaces are actually gapless with a single Dirac cone. So it would be interesting to know what will happen if we look at the fractional Chiral Hinge insulators and what will be the nature of these interacting faces at the top and the bottom surface. But once again, with the tools that we have right now, we are unfortunately stuck, and we cannot make any serious studies from these top and bottom surfaces. Okay, thank you.
Yeah, thank you for a really nice talk.